In mathematics, an affine space is a geometric structure that generalizes the properties of Euclidean spaces that are independent of the concepts of distance and measure of angles, keeping only the properties related to parallelism and ratio of lengths for parallel line segments. A Euclidean space is an affine space over the rails, equipped with a metric, the Euclidean distance. Therefore, in Euclidean geometry, an affine property is a property that may be proved in affine spaces. In an affine space, there is no distinguished point that serves as an origin. Hence, no vector has a fixed origin and no vector can be uniquely associated to a point. In an affine space, there are instead displacement vectors, also called translation vectors or simply translations, between 2 points of the space. Thus it makes sense to subtract 2 points of the space, giving a translation vector, but it does not make sense to add 2 points of the space. Likewise, it makes sense to add a vector to a point of an affine space, resulting in a new point translated from the starting point by that vector. Any vector space may be considered as an affine space, and this amounts to forgetting the special role played by the zero vector. In this case, the elements of the vector space may be viewed either as points of the affine space or as displacement vectors or translations. When considered as a point, the zero vector is called the origin. Adding a fixed vector to the elements of a linear subspace of a vector space produces an affine subspace. One commonly says that this affine subspace has been obtained by translating the linear subspace by the translation vector. In finite dimensions, such an affine subspace is the solution set of an inhomogeneous linear system. The displacement vectors for that affine space are the solutions of the corresponding homogeneous linear system, which is a linear subspace. Linear subspaces, in contrast, always contain the origin of the vector space. The dimension of an affine space is defined as the dimension of the vector space of its translations. An affine space of dimension 1 is an affine line. An affine space of dimension 2 is an affine plane. An affine subspace of dimension n1 in an affine space or a vector space of dimension n is an affine hyperplane. In formal description, the following characterization may be easier to understand than the usual formal definition. An affine space is what is left of a vector space after you've forgotten which point is the origin. Imagine that Alice knows that a certain point is the actual origin, but Bob believes that another point, call it P, is the origin. Two vectors, A and B, are to be added. Bob draws an arrow from point P to point A and another arrow from point P to point B, and completes the parallelogram to find what Bob thinks is A plus B, but Alice knows that he has actually computed P plus plus. Similarly, Alice and Bob may evaluate in any linear combination of A and B, or of any finite set of vectors, and will generally get different answers. However, if the sum of the coefficients in a linear combination is 1, then Alice and Bob will arrive at the same answer. If Bob travels to lambda A plus B, then Alice can similarly travel to P plus lambda plus equals lambda A plus B. Then, for all coefficients lambda plus equals 1, Alice and Bob describe the same point with the same linear combination, starting from different origins. While Alice knows the linear structure, both Alice and Bob know the affine structure, i.e., the values of affine combinations, defined as linear combinations in which the sum of the coefficients is 1. An underlying set with an affine structure is an affine space. Definition: an affine space is a set A to which is associated a vector space over a field K and a transitive and free action of the additive group of the elements of the affine space A are called points, and the elements of the associated vector space are called vectors, translations, or sometimes free vectors. Explicitly, above definition means that one has a map, generally denoted as an addition, which has the following properties: left identity, associativity, free and transitive action. For every the mapping is a bijection. These properties imply that for all the mapping is also a bijection. Subtraction and Weyls axioms. The uniqueness property allows to define the subtraction of any two elements A and B of A, producing a vector of this vector, denoted or as the unique vector in such that this subtraction has the two following properties, called Weyls axioms. There is a unique point such that, and affine spaces can be equivalently defined as a point set A, together with a vector space and a subtraction satisfying Weyls axioms. In this case, the addition of a vector to a point is defined from the first Weyls axioms. In Euclidean geometry, the second Weyls axiom is commonly called parallelogram rule. Affine subspaces and parallelism. Let us consider an affine space A and its associated vector space. An affine subspace B of A is a subset of A such that the set of all differences of any two elements of B form a linear subspace of this. Implies that B is an affine space, which has as associated vector space. The linear subspace associated with an affine subspace is often called its direction, and two subspaces that share the same direction are said parallel. Given a linear subspace V of the affine subspace is of direction V the sets, this implies the following generalization of Playfair's axiom. Given a direction V, for any point of A there is one and only one affine subspace of direction V, which passes through the point. Given a vector, the map is called a translation. It maps any affine subspace to a parallel subspace. The term parallel is also used for two affine subspaces such that the direction of one is included in the direction of the other. Affine map. Given two affine spaces A and B whose associated vector spaces are in an affine map or affine homomorphism from A to B is a map such that is a well-defined linear map equals F. This implies that, for a point and a vector one has therefore, F is completely defined by its value on a single point and the associated linear map. Fundamental example. Every vector space V may be considered as an affine space over itself. This means that every element of V may be considered either as a point or as a vector. This affine set is sometimes denoted for emphasizing the double role of the elements of V. When considered as a point, the zero vector is commonly denoted O and called the origin. If A is another affine space over the same vector space, the choice of any pointer in A defines a unique affine isomorphism, which is the identity of V and maps to O. In other words, the choice of an origin or in A allows to identify A and up to a canonical isomorphism. The counterpart of this property is that the affine space A may be identified with the vector space V in which the place of the origin bar been forgotten. Affine combinations in barycenter. Let us consider, in an affine space, n points A1, and n elements of the ground field. For clarity, we denote the vector B, A, if for any 2 points O and O1 has. Thus this sum is independent of the choice of the origin, and the resulting vector is denoted in particular, when one retrieve the definition of the subtraction of points. If let us denote by the unique point such that for some choice of an origin one can show that is independent from the choice of the origin. Therefore, if one writes the point is called the barycenter of the for the weight, one says also that is an affine combination of the with coefficients. Examples. When children find the answers to sums such as 4 plus 3 or 4 minus 2 by counting right or left on a number line, they are treating the number line as a one-dimensional affine space. Any coset of a subspace V of a vector space is an affine space over that subspace. If T is a matrix and B lies in its column space, the set of solutions of the equation Tx equals B is an affine space over the subspace of solutions of Tx equals 0. The solutions of an inhomogeneous linear differential equation form an affine space over the solutions of the corresponding homogeneous linear equation. Generalizing all of the above, if D VW is a linear mapping and Y lies in its image, the set of solutions xv to the equation Tx equals Y is a coset of the kernel of T, and is therefore an affine space over Ker T. The space of complementary subspaces of a vector subspace V in a vector space W is an affine space over Hom. That is, if is a short exact sequence of vector spaces, then the space of all splittings of the exact sequence naturally carries the structure of an affine space over Hom. Affine span and bases. For any subset X of an affine space A, there is a smallest affine subspace that contains it, called the affine span of X. It is the intersection of all affine subspaces containing X, and its direction is the intersection of the directions of the affine subspaces that contain X. The affine span of X is the set of all affine combinations of points of X, and its direction is the linear span of the X, Y for X and Y in X. If one chooses a particular point x0, the direction of the affine span of X is also the linear span of the X, x0 for X in X. One says also that the affine span of X is generated by X and that X is a generating set of its affine span. A set X of points of an affine space is said affinely independent or, simply, independent if the affine span of any strict subset of X is a strict subset of the affine span of X. An affine basis, or barycentric frame of an affine space is a generating set that is also independent. Recall the dimension of an affine space is the dimension of its associated vector space. The bases of an affine space of finite dimension n are the independent subsets of n plus 1 elements, or, equivalently, the generating subsets of n plus 1 elements. Equivalently, x0, xn is an affine basis of an affine space if and only x1, x0, xn, x0 is a linear basis of the associated vector space. Coordinates. There are two strongly related kinds of coordinate systems that may be defined on affine spaces. Barycentric coordinates let A be an affine space over a field K of dimension n, and be an affine basis of A. The properties of an affine basis imply that for every X in A there is a unique tuple of elements of K such that and they are called the barycentric coordinates of X over the affine basis if the Xi are viewed as bodies that have weights. The point X is thus the barycenter of the Xi, and this explains the origin of the term barycentric coordinates. The barycentric coordinates define an affine isomorphism between the affine space A and the affine subspace of knots plus 1 defined by the equation for affine spaces of infinite dimension. The same definition applies, using only finite sums. This means that for each point, only a finite number of coordinates are non-zero. Affine coordinates. An affine frame of an affine space consists of a point, called the origin, and a linear basis of the associated vector space. More precisely, for an affine space A with associated vector space, the origin O belongs to A, and the linear basis is a basis if, for each point P of A, there is a unique sequence of elements of the ground field such that or equivalently they are called the affine coordinates of P over the frame. Example: in Euclidean geometry, Cartesian coordinates are affine coordinates relative to an orthonormal frame. That is an affine frame such that is an orthonormal basis. Relationship between barycentric and affine coordinates. Barycentric coordinates and affine coordinates are strongly related, and may be considered as equivalent. In fact, given a barycentric frame, one deduces immediately the affine frame in. If are the barycentric coordinates of a point over the barycentric frame, then the affine coordinates of the same point over the affine frame are conversely. If is an affine frame, then is a barycentric frame. If are the affine coordinates of a point over the affine frame, then its barycentric coordinates over the barycentric frame are therefore barycentric, and affine coordinates are almost equivalent. In most applications, affine coordinates are preferred, as involving less coordinates that are independent. However, in the situations where the important points of the studied problem are affinity-independent, barocentric coordinates may lead to simpler computation, as in the following example. Example of the triangle. The vertices of a non-flat triangle form an affine basis of the Euclidean plane. The barocentric coordinates allows to characterize easily the elements of the triangle that do not involve angles or distance. The vertices are the points of barocentric coordinates, and the lines supporting the edges are the points that have a zero coordinate. The edges themselves are the points that have a zero coordinate and two non-negative coordinates. The interior of the triangle are the points whose all coordinates are positive. The medians are the points that have two equal coordinates, and the centroid is the point of coordinates. Change of coordinates. Case of affine coordinates. Case of barocentric coordinates. Properties of affine homomorphisms. Matrix representation. Image in fibers. Let be an affine homomorphism. The image of is the affine subspace G of, as an affine space does not have a zero element, and affine homomorphism does not have a kernel. However, for any point x of F, the inverse image F1 of x is an affine subspace of E, of direction G1. This affine subspace is called the fiber of X. Projection. An important example is the projection parallel to some direction onto an affine subspace. The importance of this example lies in the fact that Euclidean spaces are affine spaces, and that this kind of projections is fundamental in Euclidean geometry. More precisely, given an affine space E whose associated vector space is V, let F be an affine subspace of direction W, and D be a complementary subspace of W in V. For every point x of E, its projection to F parallel to D is the unique P in F such that this an affine homomorphism whose associated linear map Q is defined by the image of this projection as F, and its fibers are the subspaces of direction D. Quotient space. Although kernels are not defined for affine space, quotient spaces are defined. This results from the fact that belonging to the same fiber of an affine homomorphism is an equivalence relation. Let E be an affine space of associated vector space V, and D be a linear subspace. The quotient T, D of E by D is the quotient of E by the equivalence relation. This is an affine space, which has V, D as associated vector space. For every affine homomorphism, the image is isomorphic to the quotient of E by the kernel of the associated linear map. This is the first isomorphism theorem for affine spaces. Affine transformation. Axioms. Affine space is usually studied as analytic geometry using coordinates, or equivalently vector spaces. It can also be studied as synthetic geometry by writing down axioms, though this approach is much less common. There are several different systems of axioms for affine space. Coxeter axiomatizes affine geometry as ordered geometry together with an affine form of Desargues's theorem and an axiom stating that in a plane, there is at most one line through a given point not meeting a given line. Affine planes satisfy the following axioms. Any two distinct points lie on a unique line. Given a point and line, there is a unique line which contains the point and is parallel to the line. There exist three non-collinear points, as well as affine planes over fields. There are also many non-Desarguesian planes satisfying these axioms. Gives axioms for higher dimensional affine spaces. Relation to projective spaces. Affine spaces are subspaces of projective spaces. An affine plane can be obtained from any projective plane by removing a line and all the points on it, and conversely any affine plane can be used to construct a projective plane as a closure by adding a line at infinity, whose points correspond to equivalence classes of parallel lines. Further, transformations of projective space that preserve affine space yield transformations of affine space. Conversely, any affine linear transformation extends uniquely to a projective linear transformation. So the affine group is a subgroup of the projective group. For instance, Mobius transformations are affine if and only if they fix the point at infinity.